When you do that, the amount of computation is 42.5 exaflops. Now, how impressive is this number? It's said to be 24 times the computing power of the largest supercomputer in the world. Hello everyone, nice to meet you. This is Yeol Ah. At Google Cloud Next, there were many AI announcements. If I were to summarize them in this video, there would be a lot of content. But what I particularly focused on was the new generation of TPUs, specifically the 7th generation TPUs, codenamed Ironwood. It is expected to be released in the second half of the year under the name V7P. In terms of performance, it has increased by 3,600 times from 2018 to 2025. Over the past 7 years, Google's custom chips have expanded by a staggering 3,600 times. These improvements have been made with each generation, particularly the Ironwood, which is comparable to the H200, NVIDIA's best-selling GPU at the moment. When compared to NVIDIA's performance, it is nearly identical. However, it is much better in power efficiency. Additionally, there was a brief mention of the Willow chip related to quantum computing. However, today, I want to focus on why Google's customized TPUs are regarded as the most advanced among big tech companies' custom chip designs. We'll explore the progress made with each generation and how Google has meticulously prepared everything from software and OS platforms to AI platforms and hardware design. So let's dive right in. First off, take a look at this board. You can see 4 Ironwood chips mounted on it, right? It's an impressively large board. To start with, Google's current strategy seems to be focused on undertaking virtually everything related to AI technology. Google is releasing its own Gemini series models. These can be updated and run on devices. For example, Project Astra could be applied in real time on a Galaxy device. From on-device AI to the newly introduced Gemini 2.0 Pro, Google has initially used NVIDIA's AI chips for training and inference, but it's important to note that it was Google who originally proposed the transformer model. TPUs were designed even before the introduction of transformers. Back then, it was based on a fully connected network. With CNNs, it was adjusted accordingly. Then, they adapted it to transformers, designing Ironwood to maximize performance while reducing power consumption. They claim it achieves performance comparable to the H200. According to Google, this is how they introduce it. The Ironwood is Google's first TPU. But what kind of first TPU is it? This is the first TPU specifically designed for the inference era. In essence, as we enter the age of AI services and agents, the need for inference on Google Cloud is expected to surge. This TPU has been optimized to perfectly meet those demands. Here's what's truly fascinating. Over 9,216 chips are cooled using liquid cooling. This allows the chips to interconnect up to 9,200 units. This indicates that numerous units can be linked together to handle enormous models at once, and there's a renewed interest in these mixtures of experts. When you gather multiple experts, the total number of parameters becomes huge. But during inference, only a portion is activated. Since only the required experts are activated, it allows for more efficient power usage. However, during training, these models are so massive that combining them consumes a lot of power, and continuous training leads to various issues, such as networking bottlenecks, causing some parts to remain idle. But these issues have been largely resolved in the past 2 to 3 years. As a result, Google, which had adopted the MoE architecture early in the Gemini series, has made significant optimizations to ensure that it can handle tensor operations very efficiently, including matrix and vector calculations. When this expands to 9,216 chips, that's per pod. They really pack in a lot of chips. This results in a computational power of 42.5 exaflops. Now, how impressive is this figure? They say that the computing power of this supercomputer, called El Capitan, is 24 times greater than the largest in the world. Isn't that incredible? It's 24 times more powerful than the toughest computing system today. But actually, this is a bit controversial. El Capitan is based on FP64. This supercomputer uses FP64. The TPU's 42.0 exaflops is measured in FP8. FP8 has no standard computation metric, so saying it's 24 times more powerful is not entirely accurate. Such a comparison isn't quite right. But considering the growing use of FP8 in the AI market, it's roughly 24 times faster than the leading competitor. Each chip boasts a peak performance of approximately 4,600 teraflops. Considering this figure, we need to check NVIDIA's current numbers. The H200 series has several models. Looking at the H200, an FP8 tensor core reaches nearly 4,000 teraflops. Each of Google's chips delivers 4,600 teraflops, which means that per chip, it slightly surpasses the H200. So, scaling this up to a pod with 9,200 chips results in 42.5 exaflops. To compare, NVIDIA's configuration with 256 DGX systems in a pod, and considering that a superpod includes 32 DGX systems, would have a total of 256 H200 GPUs, achieving roughly 1 exaflop. So, from a scalability angle, we can see how well Google structured their supercomputer to achieve the vast 42.5 exaflops with their TPUs. Additionally, the SparseCore, which has been integrated since TPU version 5, is utilized in ranking and recommendation systems. In the case of Google, they have a huge demand for determining which results to show at the top during a search. Therefore, they have long utilized TPUs to figure out what to recommend first. This also applies to various other features on the Google platform. These tasks are efficiently handled by hardware, and when managed by software and CPUs sequentially, the process remains swift. So they introduced this SparseCore to speed things up, and this time they upgraded it to improve performance. Google's TPU version 2 was nearly a prototype. The first real application was with version 2. From there, it increased 10-fold, 100-fold, and 350-fold. Compared to TPU version 5, it has grown almost 10-fold. And to connect all these pods, which number around 2,200, you need an interconnect called ICI. NVIDIA uses NVLink or Ethernet-based InfiniBand to connect everything, enhancing throughput between chips, and Google has also improved their links to 1.5 terabits per second, a significant boost from the previous trillion. Like NVLink, speeding up inter-chip communication is something Broadcom and Google are likely working hard on. It's truly impressive. Connecting 4,800 units in V4 was already a lot. V5 doubled that. Now Ironwood connects up to 9,200 units. This appears to be utilizing the HBM3E technology. Look closely at the Ironwood chip. You can see 8 HBM3Es attached on both sides. 1, 2, 3, 4 on each side. Can you see it clearly? It's slightly divided into two parts. This means it's made of interconnected chiplets, not a single chip. As you can see, it's limited by the reticle size. Based on the reticle, the approximate maximum size of this chip is about 858 square millimeters. To create a massive chip, they made each part separately. This is the H2 MOS, where two of them are created and interconnected. This one also has HBM attached on both sides. Combining these two in Google's Ironwood exceeds 858 square millimeters. In other words, packaging is now essential for high-performance server semiconductor chips. This could be done by linking the HBM with the TPU processors, or later, using TSMC's technology to stack them like so I see. It seems that this packaging will be a standard feature, providing 24 gigabytes per unit and totaling 192 gigabytes with 8 units. This robust HBM capacity per chip also requires these units to interconnect with each other. So the internal bandwidth must increase. Each link needs to be very fast. After creating one board, it connects seamlessly to others. The reason we use liquid cooling here is because the heat output is extremely high. As I often mention, it's commonly called water cooling, but technically, that's not accurate. Since we're not using water, the term water cooling isn't quite right. However, we use liquid cooling because immersion cooling tends to be more effective. In this cooling technique, oil moves over the chip, drawing the heat out and expelling it. Another method involves using a rear door system to extract heat from the back of the chip, which is quite commonly used. That said, switching to immersion cooling allows for significantly better heat dissipation, as it involves fully submerging the chips in oil. To design such a structure, the data center building needs a complete redesign. When leveraging existing data centers, liquid cooling is the necessary interim solution. Therefore, in the case of Ironwood, it should be understood that it is utilizing liquid cooling rather than immersion cooling. Timothy Morgan wrote an in-depth article in the Next platform, thoroughly analyzing each generation. He provided a comprehensive summary, though many details remain undisclosed. However, looking at the significant differences from the previous support, considering 445 twice, it totals almost 900. With 892, it was hard to use one chip. The number of transistors increased a lot. Every time the number increases by 3 to 4 times, and this time it's 274.4 billion transistors. That's an enormous number. For reference, the H200 has 80 billion transistors. Blackwell has 280 billion, but the TPU has 274.4 billion transistors. That's more. The two chips are dual bonded, so the clock speed is slightly reduced. You can see that the external HBM memory is HBM3U with much larger capacity than before. This Ironwood will likely be named V7P. It's expected to be released in the fourth quarter this year. It now supports FP8, which was previously unsupported. As S8 is used more for inference tasks, it seems Google refers to this as their first TPU designed for the inference era. Actually, TPUs were designed for inference from the start. The first Google TFDA is for the inference era. It's somewhat a marketing term, but it includes matrix multiplication and embedding processors, so it can be described this way. Now, Google uses TPUs for training. This is replacing many tasks done by NVIDIA GPUs. Feeling threatened by this, NVIDIA is reportedly considering developing its own custom chips. What's impressive is that Google has been designing this for almost 10 years. This gives them a strong edge in AI chip design. Not many others are doing it at this level. As for Apple, although they are more focused on processors rather than AI chips, it feels like they are still a bit behind. Actually, regarding training and inference, training involves pulling in data all at once and then it's done. Of course, every time you train, a lot of data is involved, but it typically concludes in one shot. When it comes to inference, the more users and AI agents interact and utilize the system, the more this chip will operate without any limits. Since it consumes a lot of power, the more you can reduce the cost, the more it directly translates to your operating profit. Google realized this early on. They decided to to create something specialized. In reality, for YouTube video encoding and decoding, Google has created dedicated hardware accelerators. This method is significantly more cost-effective compared to processing everything on AMD or Intel CPUs, or occasionally using GPUs, as the custom chip design can swiftly and efficiently handle the specific format. With Google's acquisition of YouTube and its expansion in that domain, they were quick to recognize the potential. As time goes on, Google can increasingly capture parts of the market that NVIDIA's GPUs currently hold. However, Google does not sell these TPUs to other companies. Instead of marketing their TPUs directly, Google is making them more accessible and affordable through Google Cloud. So if this becomes cheaper, developers will use this TPU for their projects. Moreover, this cost efficiency has the potential to bypass NVIDIA's hefty margins, resulting in more optimized and effective data centers. This can boost profit margins. They are working on interconnect technology with Broadcom, so they are likely gaining a lot of hardware expertise. Therefore, from AI models to software, AI services, and agent models, I recently shared a video on how to integrate them all. Moreover, with their hardware in place, Google is building a strong and comprehensive AI full stack. Initially, there were issues like delayed releases, poor reception of Bard 2, and allegations of bias, which can be attributed to the rushed nature of the service rollout. However, it seems that Google has been steadily preparing its secret weapons, and we're starting to see the results. Thus, we can observe the progression from BF16 to FP8, and eventually we will see even lower precision units like INT4. Consequently, the data transfer rates per pod per second have seen a remarkable boost, positioning Google to maintain a strong edge in both supercomputing and service delivery. While other major technology companies are also in the process of designing their own custom chips, it is evident that Google, having made early investments in this area, is now in a position to demonstrate a significant lead, as showcased in their recent Google Cloud announcement.